Hello.
Oh, there's Andrew. Okay.
Hey, Tyler, sorry, I'm jumping between a plumbing emergency and other meetings, so I'm a little late today. But how's it going?
I don't see any water.
No,
Can't be
not
that
in here,
bad.
Fortunately, just elsewhere. But, all right. Let's see. Do you want to try sharing your screen, Tyler, just to be sure that that works okay?
Yeah, let's do that. So share. Okay, can you see this?
Yep, that looks good.
And then let's try, is it now in the presenter view?
Yep, yep,
Cool.
nice and clear, looks great.
And can you see my mouse?
Yep.
Cool.
Good, all looks good. And we usually record these talks. Are you okay with that? It's just for people to watch later if they can't make it.
Yeah, perfectly fine with that.
Okay, excellent. Great. So we'll give it a couple more minutes for people to join.
Yeah, sounds good.
Okay. Okay, I think more people still joining. Hold on. Okay. Okay, so I think we can get started. So it's a pleasure today to welcome Tyler Holland-Ashford to give our lunch seminar. Tyler's a grad student at The Ohio State University, working with Laura Lopez. His work focuses on using X-ray observations to understand supernova remnants, and he's going to tell us today about investigating the ejecta asymmetries. So, Tyler, take it away.
Great, yeah, thanks for that introduction. So yep, I will be talking to you about some of the work that I've done and also some of the work other people have done in studying ejecta asymmetries in supernova remnants. So for a brief outline of my talk, I'll start out with background of supernova and supernova remnants. Then I'll talk about the relationship between ejecta asymmetry and neutron star kick velocities and what that can tell us about explosion mechanisms and progenitor scenarios. Moving on to then the asymmetries of individual elements in supernova remnants, your oxygen, magnesium, iron, and how the differences between those can inform our understanding. Then I'll talk to you about a novel method for analyzing supernova remnants, the GMCA method, which I'll define later. And then finally moving on to future work that I have and also new telescopes and how that can help us understand supernova remnants. And so at its most basic, right, supernova are the explosions of massive stars or white dwarfs, and they are incredibly important for so many things in understanding the universe. They synthesize heavy elements. Here is a nice periodic table of element synthesis from Jennifer Johnson at Ohio State. When you can see the green and cyan corresponds to elements synthesized in core collapse or type 1a, right, from massive stars or white dwarf explosions, respectively. Supernovae, everything from carbon to up to iron and past even beyond that a little bit, is predominantly from supernova explosions. And these elements are synthesized during and then are ejected outward and mix with the ISM. Supernovae are also important for imparting energy into galaxies. They aid in creating super bubbles, such as this one right here, a mix of of the pressure from massive star winds, and then also supernova remnants as their shocks and energies propagate into the environment. And supernova can also regulate feedback through imparting said energy and making it less likely for stars or molecular clouds to collapse into stars. Supernova remnants are thought to be a source of cosmic ray acceleration, as ISM electrons and protons are bounced back across the forward shock and accelerated to very high energies. Supernovae are thought to be very important for dust destruction and creation. Here's a simulation of supernova 1987A, the shock wave plowing through and destroying dust, and the dust reforming. So the amount of dust that is created or destroyed in supernova remnants is a hot topic. And of course, supernovae are useful for cosmology, studying the expansion of the universe using type 1As as standard candles to measure expansion, and so many more things that I haven't mentioned. The problem with studying supernova directly is that it can be difficult due to their rarity. Even though they're so bright that they can almost outshine an entire galaxy, their frequency of about 2 per galaxy per century is low enough that we only see a lot of them from faraway galaxies. Right? We were lucky to have a supernova explosion 1987A in the Large Magellanic Cloud, but we haven't seen one in the Milky Way for hundreds of years. And this, of course, limits our understanding because you can't get as detailed observations as you want to, and there's still a lot of things that are uncertain about explosion mechanisms and progenitor scenarios. What type of star turns into what type of explosion, and what are the physical processes that that happen in explosion, and that lead to any asymmetry or element synthesis, etc. And so for that, I like to look to supernova remnants. Supernova remnants are the leftovers from supernova explosions as they expand throughout the surrounding medium, and these objects are visible for tens of thousands of years. So even though we haven't seen an explosion in the Milky Way for hundreds of years, we can still see hundreds of supernova remnants in various wavelengths. And because they're in our galaxy and they've been expanding for tens of thousands of years, they are, on the size of parsecs or tens of parsecs scale. And with high resolution telescopes, you can observe them and really resolve the structures present within these supernova remnants. And so here is the supernova remnant Cassiopeia A, one of the most well-known core collapse supernova remnants. It's pretty young, only 340 years old, 300, I guess 50 now. And here is a composite X-ray image. And not only can you see just the overall structure of this remnant from looking at this image, each color actually corresponds to a different emission process or a different emission from different elements in this remnant, because when you observe an X-rays, you get the photon energy, which corresponds to, say, iron emission lines or synchrotron emission. So in this image, the orange and green are from silicon and sulfur. The purple magenta is from iron emission, and this blue is from synchrotron emission from the forward shock. And you can really look at all of these different aspects individually in supernova remnants, and then compile all this knowledge together to increase our understanding of supernova remnants, and thus back evolving that to understand more about supernova explosions. So one detail I've focused on in my analysis of supernova remnants is their asymmetries. So here on the left is just a sample of 6 somewhat randomly chosen supernova remnants, mostly because they look nice in pictures. And looking at them, you can just immediately see the different large scale differences between these remnants. Cassiopeia A has a more circular outward edges. W49b has this bar in the middle of it and is kind of smushed, more elliptical. Tycho is very circular but has lots of little clumps inside of it. Each remnant exhibits its own distinct levels of asymmetries, and not only large scale, as I mentioned before, these different colors can correspond to different wavelengths or different emission processes or different elements. And within a single remnant, the different colors exhibit different levels of asymmetry. And so studying all of these features can help us. And here on the right is a plot that my advisor, Laura Lopez, made in 2011, when she was looking at the asymmetries of remnants, and by measuring the multipole moments of these remnants, which are basically higher order terms of the dipole moment, right? P1 would be the dipole moment, P2 is the quadrupole moment and how elliptical a source is, and P3 is mirror asymmetry. If you kind of flipped it across its central axis, how different would the two sides look? And by performing these measurements on a sample of supernova remnants, she was able to easily see that there is a distinction between core collapse remnants and type 1a, in that core collapse remnants are systematically more asymmetric than type 1a supernova remnants. And this is pretty huge for our knowledge of supernova remnants, because it implies that there must be some process associated with these core collapse remnants that generates these asymmetries that is not present or is present to a lesser extent in type 1a supernova remnants. And so that's somewhat the motivation for a lot of my work, is narrowing down on these reasons why and seeing if we can figure out what are the reasons for these asymmetries and what that can tell us about explosions. So as I said, this is what I've been working on, mainly in X-rays. X-rays are great because they are direct probes of ejecta, whereas other elements probe more of the other wavelengths probe more of the synchrotron radiation or the unshocked ejecta or dust in supernova remnants. But X-rays primarily probe the ejecta that is shock heated by the reverse shock as it propagates inward to the remnant. These elements are heated to millions of degrees and thus emit in X-rays. And so I analyze supernova remnants in order to try to compare them to the predictions of various 3D simulations to test supernova mechanisms, progenitor scenarios, and possibly the effect of the environment. Say if you're expanding into a molecular cloud on one side and not the other side, that would of course affect your expansion. And so it's only in really the recent past couple of years where 3D simulations have advanced to the point of being able to evolve a progenitor star through explosion and then out to thousands of years in its remnant phase. This is pretty difficult to do, especially given the vastly different scales you have to consider. During an explosion, right, you have to care about the incredibly tiny scales, whereas then expanding through the supernova remnant, they expand over parsecs, so you have to go up to huge scales. So modeling both of them with the same or linked simulations can be pretty difficult. But especially in this paper by Orlando et al. 2020, they were able to take a Cassiopeia A like progenitor, evolve it through explosion and then outward. And here is just this middle non faded out image of the iron ejecta in Cassiopeia A at its current age, compared to this far right image of what we actually see. And it shows it does a very good job in recapturing the three-plumed structure of iron, where you have this left plume, this right plume, and then this northern plume. And right, these simulations are showing that this northern plume is redshifted, moving away from us, and that actually matches what we find. So 3D simulations are really just entering the era where they can match supernova remnants, and thus we can directly compare the two. So to step sideways for a little bit.
Tyler, can I ask about?
Yeah.
Sorry.
Go
so
ahead.
Maybe I missed it for a second. So how many simulations do you have to run to find something that looks like this? It just happens to look like it, or do you run a whole suite of these things, or how does that work?
Yeah, I mean, so they've throughout papers throughout the entire 2010s, simulators like Orlando and Wong with Thanarat and Thomas Janka have been running various simulations using slightly different physics, slightly different progenitor scenarios, and by kind of matching the what we know about Cassiopeia A's progenitor, and also somewhat doing some fine tuning to pick the simulation that looks most like Cass A. They were able to get something like this.
I see. Okay, and this was a type 2b. Was there anything particular about the simulation to connect it with that sort of progenitor, or is it kind of agnostic to those sort of details?
Yeah, good question. So there is, I mean, the simulation can depend on a lot of things, right? You have to care about mass and metallicity and progenitor wind. So of course, for type 2b, it's thought to be, it initially is running into a dense CSM, and you can see the hydrogen, and then that kind of falls off. So including that was important for modeling Cassiopeia A, although I don't actually think they included that in this simulation. Like, so they still haven't gotten to the point of modeling material the supernova remnant is running into.
I see. Okay,
But otherwise, yeah, it'd be like a mass argument, and I don't think there's any rotation.
Okay, thank you.
Yeah, good question. Yeah, I guess I didn't say this earlier, but feel free to chime in if you have any question instead of saving them all for the end. But yes, taking a step somewhat sideways to neutron stars. Neutron stars, the compact objects left over in some core collapse explosions. Core collapse explosions can either leave behind, right, a neutron star or a black hole. But we can, see neutron stars, and so that's actually one way we can type supernova remnants fairly easily. If you find a neutron star within the supernova remnant, and it's clearly interacting with the remnant ejecta, then that's pretty good evidence that it's a core collapse. But aside from that, we've been able to observe that these neutron stars are moving at velocities of hundreds to up to 1,000 kilometers per second. And on the right here is just showing a distribution of observed neutron star velocities. And importantly, these velocities are too fast to come from any progenitor motion, or too fast to come from, say, the disruption of a binary after explosion occurs. And so the conclusion is that they must come from supernova processes. Something in the supernova explosion process is kicking these neutron stars to these high velocities. And for a while, the two dominating theories have been a conservation of momentum like argument, either conservation of momentum with anisotropic neutrino emission, where the bulk of neutrinos are emitted in one direction, and thus due to conservation of momentum, the ejecta elements and the neutron star are kicked in the opposite direction, or we don't really care about neutrinos, and it's just conservation of momentum between the neutron star and the ejecta, where the ejecta moves in one direction and the neutron star the other. And as you might be able to tell, these have opposite predictions when you compare the neutron star's direction with ejecta. And this would be a pretty good, so looking at the correlation between these two things would be a pretty good test of which of these mechanisms dominate. And for a while, right, I said these two are the dominating theories, but for the simulations in the 2006, 2015 started moving more toward the conservation of momentum with ejecta argument, simply because it required too high energy and too much asymmetry in the neutrinos in order to generate a sufficient neutron star kick via the other method. But simulations that have made use of conservation of momentum with ejecta have been able to successfully generate neutron star kicks of hundreds of kilometers per second in what Athena et al. 2013 called the gravitational tugboat mechanism. The neutron star is most accelerated in the direction of the slowest moving ejecta, because then the slowest moving ejecta is the closest and feels the strongest gravitational force. So in this cartoon on the left, you have the bulk of ejecta motion, bulk of ejecta energy moving to the left, the slower ejecta moving toward the right, and then the neutron star is pulled along in that direction. And on the right here are just two results from their 3D simulations, where the orange arrow is the neutron star kick and the green is the bulk of ejecta. And as you can see, the neutron star is moving in the opposite direction as most of the ejecta. And so, but of course, this was just theory. This was just simulations, and so this need to be tested to see if we actually saw it in reality. And so one of my first projects was to test this correlation and gather a sample of young supernova remnants, young so that they had not yet had time to interact much with any inhomogeneous environment. Of course, these remnants need to have detected neutron stars, and importantly, with neutron star velocities to compare the neutron star motion with the ejecta motion. And I want to take a little bit of time to discuss the various methods of estimating neutron star velocities, because it's somewhat important to use the right method, or at least understand the errors of each method. So one of the most straightforward is the proper motion method. You just measure the neutron star motion as it moves across the sky. Uh, Pretty simple, but unfortunately, you kind of somewhat need long baselines to do so over even with some of the best even with Chandra, the X-ray telescope with the best spatial resolution at a sub-arc second spatial resolution, you still need more than 10, 15 years in order to get robust velocity estimates. Here's an example of analysis done on a neutron star in Puppis A, and as you can see, with 7 years, they got a pretty large velocity with still a pretty large error, and it really took 10 to 20 years before they could nail down on a fairly precise velocity measurement. And so this method is good, but it just requires a long baselines. Another method is the geometric method, which is the easiest to do in that you estimate the geometric center of the supernova remnant by basically guessing by eye, drawing a circle around the remnant and trying to guess how well that circle fits the remnant, and then the center would be that explosion site. And then you take the distance between that explosion site and the current measurement of the current location of the neutron star, and that gets you how far it's traveled. The issue, as I highlight in this image here, so this is a supernova remnant, IC443, and depending on your preference, you could say that the center is the center of this bright region, center 1, or you could say that the center of the supernova remnant is, along this profile of this more diffuse emission, center 2. And so each one of these proposed centers is equally likely, a priori, uh, but they result in very different neutron star calculated velocities. And you're somewhat assuming a level of symmetry in the remnant that might not be true. Remember, remnants are asymmetric, so assuming it's spherical or circular is not necessarily a good estimate. Unfortunately, right, this is the easiest method because you don't need any type of detailed observations or calculations, and so this is one of the most common ones. But a lot of the neutron stars that have reported velocities of above 1,000 kilometers per second are from this method and thus might not be accurate. And then finally, a third method, which I find the coolest, is to actually calculate the supernova remnant explosion using the proper motion of various filaments in the supernova remnant. Just you watch the entire supernova remnant over a time period of 10 to 15 years. You track a bunch of different ejecta filaments as they move outward, and then you back evolve all of them to a central point. And so this has been done successfully in supernova remnants Cassiopeia A and G292, shown here. But of course, in order to do this method, you require to actually get these measurements of these very different filament motions, and also requires a long time. But a benefit of this is that you then also get the details about the velocities of these ejecta, which can help measure the energetics and properties of the supernova remnant itself. And then you also get a measurement of the explosion site of the supernova, which can help in all different kinds of analysis. So this has also been attempted for G350.1, and just here's an example of something that has not yet progressed to the point of getting a precise explosion site. Here on the right here is various filaments back evolved to their central regions, and as you can see, the regions are in nearby areas, but it hasn't resolved to a precise point, which you can claim is the supernova remnant center. So this method has had some success, but for other remnants, we need much more time and many more filaments studied. So to just recap, there's these three methods: neutron star proper motion, geometric method, and back evolved filaments. but I would only say that 2 methods are reliable. And so that is what I based my analysis on, only using one supernova remnants that had robust neutron star proper motions or supernova remnant explosion sites via back-evolved filament motion. And doing so, I was able to get a sample of 6 supernova remnants that satisfied all the criteria. And I compared the bulk motion of ejecta to the neutron star motion and got a pretty striking result where in 5 out of 6 of these supernova remnants, the neutron star seemed to be moving almost exactly opposite to the bulk of ejecta motion. Here is plotted the angle between the neutron star and the ejecta, and see 5 out of these 6 remnants are about at 150 to 180 degrees, directly anti-correlated. And this is in support of that the dominant mechanism of generating neutron star kicks is conservation of momentum with ejecta that is asymmetrically emitted due to asymmetric explosion forces in the supernova explosion, consistent with this gravitational tugboat mechanism. You have a question?
Yeah, well, could you unpack that a little more? Like Cassiopeia, like you were showing, has like 3 different plumes.
Mm-hmm.
And so is it the 3 plumes are kind of more on one side and then the neutron star is veering off in the opposite direction to those plumes, or is that the wrong intuition?
No, that's a correct intuition. Cassiopeia A does have those kind of 3 plumes. I'm going to skip forward a lot here. And right, so this is iron in Cassiopeia A, and it shows you these 3 plumes. And the neutron star is moving south-southeast, so it's about here where my mouse is, where this triangle with a star is the explosion site. And yeah, if you take into account how I calculated the bulk motion of ejecta, is I calculated the center of emission, so basically the center of mass, but just using X-ray emission as a proxy for mass. And that tended to be up here because there's like much more emission up here in this plume and basically no emission from ejecta down here.
Great, thank you. Sorry
Yep.
for making you skip ahead.
Nah, no worries. No worries. So yeah, I did that for all of these remnants, and again, showing that they're preferentially in 5 out of the 6 remnants kicked opposite the bulk of ejecta. Of course, there is this other one, RCW 103, down here, which shows a direct correlation, almost a 0-degree angle difference. A couple asterisks here about RCW 103, and the biggest one is that it has a very weird magnetar in its center. So, instead of a normal neutron star at 10 to the 12, 10 to the 13 Gauss, it has a magnetar, 10 to the 14, 10 to the 15 Gauss, and it's an incredibly slowly rotating one, about a 7-hour period compared to the typical magnetar rotational period of about 7 seconds. And so that is a hot topic in supernova remnant and magnetar studies, and that could have something to do with why it's moving in the same direction as the bulk of ejecta. So I want to also mention another paper that did this type of analysis, a similar neutron star kicked versus bulk of ejecta analysis. And I suppose this one would have also been good to answer your question, Anthony. But what they did is instead of they used a similar method where they calculated the center of X-ray emission. I guess we'll focus on this bottom left one here. These are the zoomed in regions of various supernova remnants. They identified the neutron star, found the center of X-ray emission, and used that as a proxy for the supernova remnant explosion center, and then compared that to the center of mass of the elements, whatever elements they could find, intermediate mass or oxygen or iron. And so calculating the angle between these is the same type of analysis, the direction of the neutron star compared to the bulk of ejecta. And they found a similar finding that the neutron star was moving opposite the bulk of ejecta in all of their supernova remnants, not necessarily all close to 180 degrees, but definitely not in the same direction. And they also found that RCW 103's magnetar was moving in the opposite direction of ejecta in contrast to my finding. And so that will be a very interesting result to fine tune and narrow down on in future years and see which one of these holds true and what implications that might have for how this magnetar with this very slow rotational period was formed. And so this was my first project as a graduate student. But there were more predictions of this asymmetric explosion mechanism in the simulations that was thought to lead to this neutron star being kicked opposite the bulk of ejecta. Is specifically that these asymmetric explosion mechanisms that cause the asymmetry we see in the remnants should produce a higher level of asymmetry in the heavier elements, as these elements are the ones that are formed predominantly during explosion and thus will be very strongly subject to the explosive forces. Whereas, for example, oxygen is formed primarily during hydrostatic post-main sequence burning and thus exist in shells, on the exterior-ish of the progenitor star, and thus will be further away from the strong explosive forces and thus be less asymmetric. And similarly, if the neutron star is gravitationally accelerated to the slowest moving ejecta and then it should be more accelerated to elements that are formed closer to the core of explosion and thus should be kicked most opposite to these heaviest elements. And so these are two predictions I wanted to test to see if this continued to hold true. And for this, I focused on a single supernova remnant, Cassiopeia A, as Cassiopeia A is young, so it hasn't had much time to interact with any inhomogeneous medium. And there's also megaseconds of data, so much data on Cassiopeia A, so I could really do the detailed analysis that was necessary. So to create these different maps of ejecta, a simple way is to just take the bandpass, the energy ranges associated with different emission lines of these elements. Here is an X-ray spectra of Cassiopeia A, and I've highlighted different regions that are corresponding to different elements emission lines. So this emission lines is from silicon, from sulfur in green, and then iron, and you can simply take those photons, take those maps, create them, and you get images such as these. The problem with this type of analysis is even though it's quick, you are including all this broad continuum emission, which can come from thermal Bremsstrahlung or non-thermal synchrotron. And so the maps that you're creating, yes, they include element from that emission yes, they include emission from that element, but they also include emission from other elements and other sources. And so it's not as detailed as it's not as precise as you'd like it to be. And so in order to fix this problem, you perform continuum subtraction. I analyzed as many regions as I could in Cassiopeia A, about 2,500 individual regions, extracting and fitting the spectra of each. And when you do this fitting, you can get a continuum fit. So here is the data for one of the regions in Cassiopeia A, and here is the continuum fit. And if you take the data minus the continuum, that leaves only the emission from the elements from their emission lines. And so then you can do this bandpass method on those continuum subtracted maps and get maps of each element that are coming from just the emission in question. And so right here is the the slide that I brought you to before. On the left is bandpass, where you include continuum emission. In the middle here is a continuum subtracted map, and you can just very much see you've lost a lot of the diffuse emission that was present in this bandpass map, and now it is just emission from iron. And this matches various simulations and other studies we've done of Cassiopeia A, which is known to have this three-plumed structure. Actually, here is the direction of the neutron star, this arrow here. And so doing this for the various different elements, I compared their asymmetries to each other to see if, to relate how asymmetric the different elements were as a function of mass. And again, similar to my first project, got a pretty striking result where here's the plot showing you how elliptical, asymmetric, and mirror asymmetric these elements are. Top right is more asymmetric. And it's clear that the lower mass elements, oxygen, are more symmetric than the heavier mass elements, going almost directly in like a 1-to-1 correlation going up with mass. And furthermore, they seem to be grouped by burning process. Things that are formed almost entirely during post-main sequence hydrostatic burning are very symmetric, as they are not present close to these strong asymmetric explosion forces. Intermediate mass elements, silicon through calcium, are formed primarily half during, or some parts during hydrostatic burning, and some parts during explosive synthesis. And these have this middling levels of asymmetries. And iron, for example, is formed almost entirely during explosion, and thus is most strongly subject to these asymmetric explosion forces. And then I also wanted to test, right, this is the analysis on continuum subtracted images. I wanted to see how necessary was it to perform this very detailed level of continuum subtraction. And so on the right here is the same plot, just run on the bandpass images where I did not perform continuum subtraction. And you see that the general trend is similar. Oxygen is very symmetric, iron is very asymmetric. But if you care about elements that are of the same burning process, they seem to have lost this one-to-one correlation, and thus comparing them using this bandpass analysis would probably be inaccurate. But if you wanted to compare oxygen to silicon or silicon to iron, then this bandpass analysis might be sufficient, and you don't have to do the very, very detailed spectral fitting of hundreds to thousands of different regions within the supernova remnant. So also I want to touch on the neutron star kick relation, right? This scenario that where asymmetric explosion forces cause asymmetric ejecta and heavier elements are more asymmetric should also result in the neutron star being kicked most opposite to these heaviest elements. And again, I found basically this was exactly true for Cassiopeia A. Here is a zoom in region of the interior Archimedes 2 to Cassiopeia A with the center of emissions for all of these elements labeled in X's. Neutron star is down here, moving downward from the explosion site. And you can see it's almost a 180-degree separation or difference between the neutron star motion and these heavier elements, these argon, calcium, iron, and titanium, whereas it's more of a 150-degree or less anti-correlation with these lighter elements. And so just the conclusion of these two papers, these two projects that I've worked on, along with the others who have also found similar results, such as Katsudo et al., is that you can use supernova remnant asymmetries to test explosion mechanisms, and neutron stars are in fact kick opposite the bulk of ejecta in supernova remnants, consistent with this gravitational tugboat mechanism, and in at least Cassiopeia A, heavier elements are more asymmetric than lighter elements, and the neutron stars was kicked most opposite to the heaviest elements. And so that is what I found for these two papers. And for the next part of the talk, I want to discuss the methods of analyzing supernova remnants. I touched on how I analyzed Cassiopeia A, which was performing this spatially resolved supernova remnant analysis, where I took thousands of regions, extracting the spectra on each, fitting each of them, and then putting that all together into maps of each element. But as you might understand, that can be pretty time consuming and pretty tedious, as you can do this at various resolutions, either choosing going down to 10 boxes or so, or 46, which I did for analysis of supernova remnant W49b, up to thousands for Cassiopeia A. And this is the general method of doing this type of analysis for supernova remnants if you want any type of spatially resolved analysis, which is tedious, and as I said, and also doesn't make use of the fact that adjacent adjacent regions that you choose are actually physically adjacent to each other, and thus should have similar plasma properties, unless you explicitly add that step in your code, right? Just by doing this in its base level, you're doing this analysis on each region separately. And so unfortunately, this has been one of the most common, the standard way of doing this type of analysis, fitting the spectra in each region. But I want to talk to you about this new method, this novel method, which only is really was produced in the past couple of years. The general morphological component analysis method by Adrian Picono and Fabio Serro. So this method is a blind source separation method where instead of extracting and fitting the spectra in many, many different regions one by one, it basically does that all at the same time across the remnant, simultaneously fitting all the pixels and pulling out spectral components that are common throughout the entire remnant, and then assigning a weight to each pixel to each component. So in this simple example, you have a Cassiopeia A like supernova remnant, which has synchrotron emission and thermal emission present at different levels throughout the remnant. And you tell this model to find three components, and it did successfully pull out a broad synchrotron component present throughout, a thermal component, and then also you leave one for background. But importantly, the input to this method is only the number of components. You don't say I want to fit a thermal Bremsstrahlung plasma with this level of abundances of iron and this much silicon. You don't say you don't say I want you to find a synchrotron component. You just specify the number of components, and it pulls out whatever components are most common. And so this has great potential for doing analysis of supernova remnants. And so this was from their 2019 paper was a test case using mock data as Cassiopeia A, but they've actually applied this type of analysis to two supernova remnants in the years since. And so just this past year, in Yamaguchi et al. 2021, who they were also on this paper, they were able to apply this method to the supernova remnant N103b. And they were able to identify spectral components such as the one shown in this spectra here. The black is the full spectra extracted from the entire remnant. And they told it to find three components, and it pulled out these three components as the most common throughout the entire supernova remnant. And even though these look pretty messy, they actually can tell us a lot of detail about this supernova remnant. This red component here doesn't have a lot of emission in the various emission line regions for these elements, but it does have a lot of emission in the oxygen bandpass. And so this is an indication that it's from swept up shocked material as the supernova remnant is expanding into its surrounding medium and sweeping up material. And so they label this the CSM, the circumstellar material component, and the weights of each pixel that have this component are shown in this map here. The red component, actually I think the green component is component 2, has a lot of emission in iron and not a lot for these other elements. So it's the iron-rich ejecta thought to come from nuclear statistical equilibrium achieved during explosion. And then finally, there's this third component, which has a lot of these intermediate mass element emission regions. So they label it the intermediate mass element ejecta, from thought to come from incomplete silicon burning during explosion. And so they can extract these features, which can be used to inform more detailed spectral fitting or just generally increase our understanding of where different plasma components are throughout this remnant, or any remnant that this was applied to. And a cool thing they did with this paper is that through their components and analysis of red shifts and blue shifts, they were able to kind of create a cartoon of what this remnant looks like in 3D. And there seems to be two bubbles, a red shifted and a blue shifted bubble with an iron rich component in the middle. That can describe this supernova remnant. And so that's pretty useful and pretty neat, really. Getting 3D analysis of supernova remnants is pretty difficult because analyzing regions one by one, there's not really enough spectral resolution or spectral accuracy to get red shifts and blue shifts. But when you're fitting all of the pixels simultaneously, even a small minute shift in each pixel, that if that is common throughout all of the supernova remnant, that is measurable. And so that's one of the powers of this method. And so I mentioned this has also been applied to two supernova remnants. The other is Cassiopeia A. I collaborated with them on this as kind of a follow-up, or not a follow-up, I would say, but a different method of doing my analysis of individual elements, because I mentioned this method was able to pick out different components, and the components can include emission from specific elements. And so if they specify the energy ranges, they were able to, for example, shown here, pull out emission from Cassiopeia A that was background continuum emission, that was iron emission that is red shifted, and iron emission that is blue shifted. So this is more powerful than what I was able to do doing this detailed spectral resolved analysis, because I was only able to get bulk element, not being able to distinguish between red shifts and blue shifts. And so here's just a quick slide showing all of their different elements that they were able to apply this method to, finding redshift and blue shifted maps of each of these elements. And then they were able to perform the same analysis that I did, measuring the asymmetries, and get a pretty almost exactly matching result. If we ignore magnesium, because magnesium has a lot of problems as it's close to emission lines of other elements. So what is measured as magnesium is not fully magnesium. But the other elements, oxygen, silicon, sulfur, argon, calcium, and iron K, which is what I measured, they again show this one-to-one correlation where the lighter elements are more symmetric and the heavier elements are more asymmetric. And so both of these papers on N103b and on Cassiopeia A just show the power of this method and its robustness in that it is able to produce the same results that papers doing detailed spectral resolved analysis produce, and that is an indication of its accuracy. And so on the right here is just the plot that I made to compare these two plots. But as I said, they were able to get red shifts and blue shifts, and which means they were able to provide more analysis, especially in respect to the neutron star correlation. Here are the directions and the magnitudes of each of the bulk ejecta velocities as measured by their center of mass. And as you can see, all this red shifted ejecta is moving in bulk the same direction, whereas this blue shifted ejecta seems to be moving to the left to one of that easternmost knot. And importantly, the neutron star is moving most opposite to this red-shifted ejecta, which then tells us that the neutron star is moving probably toward us. Because if it's moving opposite in 2D, then it's probably moving opposite in 3D. And this is important because it's hard to get neutron, well, it's almost impossible to get neutron star Doppler shifts because there's no lines in a neutron star spectra to measure. So you need to use these type of measurements to get them. And so this method and other methods that are able to analyze supernova remnants all at once, producing maps such as they are incredibly important for moving forward in analysis of supernova remnants so that we don't have to do this nitty-gritty spatially resolved analysis on hundreds to thousands of individual regions. And so finally, just want to talk about some future work that I'm planning to do, and then also I'll discuss some future telescopes. So I did this analysis of individual elements for the supernova remnant Cassiopeia A as somewhat of a test case to see whether this was possible and whether you could just do continuum subtracted analysis, or whether you could just do bandpass, or whether you needed to do detailed continuum subtraction. But of course, Cassiopeia A is just one supernova remnant, and it's also a weird one, right? Type 2b, which is not the most common type of supernova remnant, not even the most common type of core collapse supernova remnant. So it'd be interesting to see if this trend I found, both that heavier elements are more asymmetric and most opposed to the neutron star, is true for more supernova remnants. And so I have, in the midst of analyzing the element asymmetries of these different supernova remnants, about 8 core collapse remnants, and also adding type 1a remnants to the sample to see if the core collapse sample results matches that of Cas A, or if it doesn't, either result would be interesting. And then also including type 1as in my sample, because type 1as, remember, are found to be more symmetric than core collapse remnants. So this dependence of element on, or this relationship between mass of the ejecta and asymmetry might not hold true, or might not hold as strongly true for type 1as. And also looking at the asymmetries of type 1a ejecta could help us determine the origin scenario of these potentially double degenerate scenarios where you have 2 white dwarfs collide to explode. Those might produce more elliptical explosions than single degenerate progenitors where you have material slowly accreting from a companion star onto the white dwarf. And so that would be hugely interesting to test, and there hasn't really been a study to do that yet. Of course, there are projects unrelated to symmetry. For one thing, I'm planning on measuring the mass ratios of different iron group elements and type 1a supernova remnants, because especially the ratios of, say, chromium to iron or manganese to iron can these ratios are hugely dependent on the mass of the progenitor white dwarf. I believe it's near Chandrasekhar mass white dwarfs. So that is preferentially the single degenerate. Those have much higher ratios of manganese to iron than double degenerate. And this is because the core is more dense and you get more efficient formation of manganese. And so this will be this is something that I'm also working on and could help resolve what supernova remnants are what from what type of type 1a progenitor, and which progenitor scenario is the most likely, and which explosion mechanisms are responsible for these explosions. And then finally, to touch on future telescopes, Chrism, the X-ray imaging and spectroscopy mission, is launching in January, hopefully, 2022. And so the important part about this telescope is that it will have a microcalorimeter, which will have factors of 10s to 100 better spectral resolution than current X-ray telescopes, such as Chandra or XMM Newton. Here is showing the sample spectra or example spectra from conventional telescopes in red, and then what we expect to get from Chrism in black. And you can just see that you can resolve individual lines, whereas the current telescopes kind of blur together lines that are close together. In all of my analysis I've talked to you about in this talk so far, when I talk about any element lines, that's always coming from many, many different lines from different ions, all clumped together and not able to be measured individually. And as I mentioned in the case of magnesium, magnesium lines are very close to silicon and iron lines, and so you're not able to really resolve them with current telescopes, but with Chrism we should be able to do that. And particularly this will aid in getting 3D velocity maps from Ejecta, because along with measuring precise lines, you can then measure precise redshifts and blue shifts. And so this will be pretty powerful, and I'm very much looking forward to the data from this telescope. And then, of course, further in the future, Chrism is supposed to launch in 2022. Athena is supposed to launch in 2031, I think, possibly a little bit later than that. But this will be an even further upgrade with a microcalorimeter, much higher effective area than Chrism, as shown the blue for Chrism compared to the red for Athena, and then Chandra down here. So this will be hugely more powerful in observing supernova remnants, enabling us to observe supernova remnants with less observation time and getting better spectra. And then maybe if Lynx is chosen for the current NASA science mission, that will improve on that, basically a sequel to Chandra, with Chandra's very, very good spatial resolution, the sub-arcsecond spatial resolution of Chandra, with the spectral resolution of Athena, and getting down to a few eV spectral resolution. And so all of these telescopes together, even just Chrism and Athena alone, will vastly help in understanding supernova remnants, especially their 3D natures, which we really need to understand well in order to compare to the 3D models of supernova explosions. And I'll just leave you on this side, and thank you for having me.
Okay, thanks, Tyler. Andrew, I think, had to step out for a bit, so I will ask if anyone's got any questions.
I
Okay,
had a
Gwen.
couple of basic questions.
Oh, well, I think Gwen had her hand up first, so we'll go
Yeah,
with
sure.
Gwen first.
All right, Tyler, thank you for a very interesting talk. I did miss about 5 minutes of it, so if you addressed this question, I apologize. But I was interested in knowing if you had done any studies on the crab, and I have a personal reason for that, which is that when I was an undergraduate student, I actually did this proper motion analysis of there's like a northern chimney or jet off the Crab Nebula that's hopefully not affected by the synchrotron nebula that fills the rest of the supernova remnant. And so I was wondering if I believe the pulsar is like known well and its position is known well in the Crab. And so I was wondering if you guys had thought at all about looking into the asymmetry of that remnant, or if it's kind of off the books because it does have such a large synchrotron nebula.
Yeah, no, that is a great question. And you were exactly right with that latter statement there, is that because the Crab Nebula is so much synchrotron emission, it's very difficult to get any handle on, ejecta emission from it. And so I haven't considered it for exactly that reason. But you said that you found some ejecta emission, like a northern plume. Was that correct?
Yeah, there's a northern chimney or jet or plume or whatever you want to call it. And if you trace back the motion, you actually get the sort of historic age. So this one, the crab was seen by Chinese and other ancient astronomers and it exploded in 1054. And when you trace back the age, you get 1055 for this one northern section,
Okay.
Which seems like it's probably just the fastest moving ejecta from the system. So
Okay.
I was just curious. I mean, like it's
Yeah.
a very small fraction of the nebula compared to, the bright part. You can't all seems to be accelerated and gets a date that's much more recent. So, but I was just sort of curious because it's something I did a long time ago, but haven't thought a lot about since. So.
No, great question. And yeah, I'll take a look at that to see if I can figure out if I can do analysis on that. But yeah, I just haven't because it's so much of the pulsar wind nebula. Thank you.
Thank you.
And someone else had a question, but I didn't see who it was. Okay.
I had a couple of very basic questions. So one was like, what powers this asymmetric ejecta for such a long time? So like my intuition would be that any such asymmetry should be washed away by this pressure gradients that would be there.
Yeah, good question. So at least in the analysis I've done, I've restricted myself to young supernova remnants, which is less than 5 or 10,000 years. And at these points, they are definitely the asymmetries that you see are largely from ejecta and are still retained. As you get to older remnants, that's actually that is actually a good question. What happens to remnants as they age, and how are they infected by environment and washing out of any asymmetries? And it seems like for a lot of remnants, yes, there is still strong signatures of inherent asymmetries in even these older remnants. But then you also have asymmetries from running into, say, a molecular cloud on one side and not the other. And so that can be degenerate with any asymmetries that would be from the explosion, and that makes it more difficult.
Also, like what powers the initial, say, bipolar asymmetry? Like, is it something in the powering mechanism or?
Yeah, that is a good question. So I'm not the supernova explosion mechanisms expert. I mainly take the results of what the simulators do and compare the findings. So I can't exactly answer your question on what causes the asymmetry, but it's very much thought to be from explosion with possibly effect of progenitor versus instabilities that generate as the supernova remnant expands. So it's definitely from something explosion, some asymmetric process, but I'm sorry, I can't be more detailed than that.
Yeah, thank you.
Thank you.
Anyone else? Okay. Andrew, you're back. So I don't know how you usually close this off, but.
I'm back. Thanks, Chris, for taking over. So thanks, Tyler, for a wonderful talk. I'm disappointed I missed the last 5 minutes, but I'm sure it was as great as the rest. Thanks everyone else for joining us.
Thank you for having me.
That was great.
Yeah, thanks again, Tyler. I had to run out to deal with this plumbing issue, but it seems like Chris took over successfully. So.
Sorry that you have a plumbing issue.
It's all good. These things happen, right? So awesome. And you got to meet with, I know you met with a couple of people this morning, right?
Yeah, I met with, Tingley, Drew Newman, Alex G, and then I'll be meeting with Chris imminently.
Sounds good. All right. Thanks again.
Yeah, thank you for having me.
No problem. Bye-bye.